Now we're going through some view factor relations, which will become very helpful for us in dealing with many problems. A lot of the problems that we deal with have many surfaces, and in order to understand how much of the radiation from one surface is going to be intercepted in another, you do need to know quite a couple of view factors for every problem. There are some rules that will allow us to minimize the number of calculations or the number of relations that we're going to use. One of them is rule number one here, plane surface. In plane surfaces, if you want to know how much of the radiation from surface 1 is intercepted by surface 1, we know that if it's a plane surface, it's going to be 0. It is quite intuitive as well. The radiation goes in all directions, but it doesn't turn around and go back to the surface itself. So that would, for a plane surface, it would be 0. For also a surface that looks like a convex surface looking like 2 here, same idea. Radiation goes in all directions, but will never arrive at the surface itself. But then you would then maybe say that it never can arrive on the surface itself. For the concave surfaces, like number 3 on the lower bottom left of the slide, you see that radiation coming from one part of a surface could actually be intercepted in another part of the same surface. So it is possible that F3 to 3 in this case is actually not 0. There is some radiation intercepted by the surface itself. So you do always have to take care of the cases where you have to see if it is possible for a surface to actually have a surface I to have FII as 0, or maybe a value not 0. An example of this would be, let's say we're looking at two spheres, one inside another, a hollow sphere and another sphere inside it. And let's say the inner sphere is, we're looking at the radiation from the inner sphere that arrives in the outer sphere. So we notice that F12 is equal to 1. How do we know that? We know that from inner sphere to the outer sphere, everything that the inner sphere sees is the outer sphere. We also are using the rule number 2 on the left-hand side. We know that the inner sphere surface looks like a convex surface. So none of the radiation will arrive on its own. There's only two surfaces here, surface 1 and surface 2. So your radiation, if it can't arrive on itself, it will all have to go to the outer sphere number 2. So that's why in a case like this, we say the view factor 1, 2 is going to be equal to 1. That means the entire radiation leaving surface 1 is going to be intercepted by surface 2. Now, is that the case for 2 as well? We can't quite say that. For the outer sphere 2, radiation that is leaving the surface 2 is not always going to arrive at the inner sphere 1. It's some of it is going to be intercepted by itself, and some of it is going to be intercepted by inner sphere. So for that, we need to know more. We need to do some more calculation to figure out how much of it arrives at the inner sphere and how much of it arrives at itself. And of course, I can already imagine that it depends on how large the inner sphere is. The larger the inner sphere is, with the outer sphere being at constant radius, then I would imagine that more of the outer sphere radiation is going to be intercepted by the inner sphere. But talk about that later. There's another relation called reciprocity relation. Well, we're going back to the relations that we defined for the view factor Fij and Fji. We can always take a look at these two relations and compare them against one another. They're almost the same, on just the only difference between these two relations is AI here and AJ here. So then if I multiply both sides by AI, for example, if I multiply this side by AI and this side by AI, and if I multiplied this side by AJ, this side by, I'm allowed to do that. Then I'll cancel out this, I'll cancel out this. Then all I'm left is one side of the relations are exactly the same, which brings me to this relation. AI Fij is equal to AJ Fji. Be very careful with the subscripts. You can only write AI Fij equal to Fji Aj. So for example, when some of the new lessons we learned from this is if your areas are actually the same, for example, same area AI and AJ, your view factors should be the same. What would be the case for that? Two parallel plates facing one another, same areas. If AI and AJ of the plates are the same, their view factors should also be the same, which is in that case equal to 1 in both cases. If your areas are not the same, your view factors are also not going to be the same, which is another thing we learned from here. There's also another one called the summation rule for enclosures. Be careful that this only applies for enclosures. Sometimes we actually have to make an imaginary enclosure in order to be able to use this rule. But again, we'll talk about that in more detail once we learn all of these different rules. So if you do have an enclosure or an imaginary enclosure, that is, you have many surfaces that are closing off like the picture that you see here. We say that the radiation from 1 to 1 plus radiation from 1 to 2 plus radiation from 1 to 3, basically the radiation from 1 to all the different surfaces is going to be equal to the total radiation. The same way, I would say the fraction of radiation going from 1 to 2, fraction from 1 to 3, 1 to 1, basically from 1 to all the different surfaces, including itself, the fractions should all equal to 1. So for example, I would say that 10% of my radiation falls on my own surface, and then 20% falls on this other surface, 30% falls on that other surface, but these are fractions of a total. It can only add up to 100%. So that's why we say that the fractions should add up all to 1. Another rule that becomes very helpful sometimes is what we call the symmetry rule. Remember, the view factor is all about the orientation. The only thing that matters in calculation of view factor is orientation. So if, for example, the orientation of a surface towards another is exactly the same as another one, then we may use the same view factors for them. Let's take a look at the left-hand side picture. Seeing one looking from 1 to 2 or 1 to 3, or radiation from 1 to 2 and radiation from 1 to 3 will be exactly the same because this is a symmetrical shape. So if I find that, for example, view factor from 1 to 2, I do all the calculations and I arrive at, let's say, 35% for this case, then I would be able to say that if F12 is equal to 35% or 0.35, then F13 should also be exactly the same because they're symmetrical. So for example, in this case, F12 should be equal to F13, whatever that is. And then again, because of symmetry, I can also say that the radiation from 2 to 1 should be exactly equal to radiation from 3 to 1. Why? Because again, they are facing one exactly the same. Their orientation is the same. On the right-hand side, we also use the benefits of symmetry, exactly like the left-hand side picture. This may look like a little bit more complicated, but it's actually not that difficult. From 1 to 2, 1 to 3, 1 to 4, and 1 to 5, we should have the same view factors. So a lot that I know from this figure, I already know that 1 to 1 is equal to 0. So let's take a look there. F1 to 1 is equal to 0 because it's a flat plate, right? I know that F12 should be equal to F13, should be equal to F14, and that should be equal to F15 because of symmetry. So this is because of flat plate, and this is symmetry. What else can we say about this? Is this an enclosure or not? It is an enclosure. So I can say that F11 plus F12 plus F13 plus F14 plus F15 is equal to 1, a total of 1. I mean, the radiation from 1 can't go anywhere else other than arrive at it on its own or on the other 4 surfaces. Now, I've already said that F11 is equal to 0, and I've already said that these 4 are actually equal. So in other words, I can say that this is F12 plus, I'm going to replace this with F12 plus another F12 because they're all equal, right? F12 is equal to 1. In other words, I can say that F12 is equal to 25%, which is equal to F13, which is equal to F14 and F15. You can see with the relations that we know so far, you already can write a lot about different shapes. You don't really need to integrate all the time. You can just use some logic and like based on understanding of the view factor and actually calculate this, for example, to be 25% with really limited information. Another rule that we use is called superposition rule. In this rule, we have an area called AJ, which is this area here. This is AJ, bad handwriting. And it's divided into all these different areas. So if I want to write the relation from AI to AJ, it's much easier to deal with because AI is one area, and then I'll say the radiation from AI to AJ is basically equal to radiation to all of these little areas. But then the opposite, writing the opposite is a little bit different. So let's say AJ is this area, and I want to write the opposite relations for FJI. I can say that AJ FJI is equal to, break the AJ into all these little areas if that's possible for you, and then write this. We say that it's equal to area 1 by F1I plus area 2 by F2I plus dot 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 plus area, let's call it K by FKI plus dot 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 all the way to area NFNI. So you're basically looking at all these little areas and how their view factor towards I is. If you were to rewrite this or a little bit expand it a little bit more, you would have to write this AJ in terms of this is actually equal to A1 plus A2 plus A3 plus all the way to AN. This will become more clear when we look at it in just having two or three terms in here. So we have the three triangles. On the left-hand side, the left triangle looks like you have area 1 on the bottom and then 2 and 3 on the vertical side. So you can write, using the superposition rule, you can write F23, or the sum of all those little areas together, F23 to 1, which is this one, multiplied by the area of F23 is equal to, now break down into the little areas, A2 F21, A3 F31. Or in other words, you can now divide everything to A23 and then have this relation, or in the nicer form, it's just this relation. So this is basically what's called superposition rule. You may need to think about this a little bit more than the other rules because this may become sometimes a little bit more confusing than others. The opposite is not very confusing. The opposite is what we have here. So when you have, for example, two areas like 2 and 3, and you want to write everything with regards to F23, it becomes a little bit more confusing. But then on the other side, when we're talking about the view factor from 1 to 2 or 1 to 3, it's easier. So in this case, we could say for these triangles that A1 by F1 to the two areas 2 and 3. So area 1 by view factor of 1 to 2, 3 is equal to A1, or the part of the radiation that goes from 1 to 2, F1 to 2, plus again A1, F1 to 3. So it's basically saying that the radiation from 1 to 2 plus the radiation from 1 to 3 makes up the radiation from 1 to the sum of 2 and 3, which is intuitive and makes sense. If you have more complicated shapes, there are view factor tables that you could use. They're generally categorized into two-dimensional geometries and three-dimensional geometries. Two-dimensional geometries are listed in table 13.1, and one example is shown to you here. For example, this is for an infinite plane and a row of cylinders. Depending on the spacing between the cylinders and the diameter of the cylinders, depending on these, you will be able to calculate the view factors. But these are what we call two-dimensional geometries. For three-dimensional geometries, you also have tables, table 13.2. Again, another example is given to you. This is not the only table that you have. You have to actually go to your textbook to see all the different cases that you have for view factors. So one is given to you here based on for example, surface I and J based on the spacing of these two, L, and some other information. For example, the radius of I and J, you will be able to calculate some other parameters like the R values and the S values that go into your relations, and you'll be able to calculate your Fij based on the figure here, or based on a relation that's given to you.